we want to find reactions at A and B. But now we have to contend with the distributed load before we can get there. And we're given just the figure. We start in the same place that we always do for equilibrium problems. We're going to start with the free body diagram, and we're going to see how do we model the system with the distributed load in our free body diagram. So I'm going to choose the beam as my object of interest. At B, I have a pin, so I model that just like I have in the past. At A, I have a roller. I model that the same way. The distributed load I now want to model or simplify to point loads, because those are going to be easier to handle when we get to our sum of forces, sum of moments equations. In this case, I can look at it as it's a trapezoid from A to B, but I'm going to recommend break it down into even simpler shapes. Looking at the problem, I have a right triangle that goes from A to 6 feet to the right of A, and then from that point to B, it's just a rectangular load. So I can break this down into two different shapes and simplify each of them into a single load at a single point. But I have to find for each of those shapes what should that load be and where should I locate it. Let's look at the rectangular part first. So the height of the shape, which is equal in this case to the intensity, is 150 pounds per foot. And this shape has a width we can consider of 8 feet. Just like we looked at for the solid shapes or the sheets of shapes, the equivalent force of this distributed load from 6 feet to the right of A to B is going to be the area under the shape, or the area of the shape. In this case, the rectangle is going to have an area of its base times its height. So 150 pounds per foot times 8 feet is going to give us a force with its units in pounds in this case. For the rectangle, base times height, we get an equivalent force of 1,200 pounds. For the rectangle, we know from the other day that the centroid of it is going to be at the center, the halfway between, or half of its base. It's 8 feet long, so half of its base, so from either edge, it's 4 feet. This is where we can put the equivalent force at that equivalent location. Again, the roller at A, the pin at B doesn't know the difference if it was a distributed load or if we just had a 1,200 pound weight that we set 4 feet between this point and B. The pin and the roller are going to be affected exactly the same. If we also include then the triangular part. Any questions about the first part? So this was a simplification of the rectangular portion to a point load at an equivalent location. We then move on to the triangular load. So it has a base of 6 feet, and the right triangle starts at 0 and goes up to 150 pounds per foot. So we want to find the area of that triangle will be 150 pounds per foot times 6 feet divided by 2, since it's a triangle. The equivalent force, therefore, is 150 times 6 over 2, or 450 pounds. We know for a right triangle that the centroid is 1/3 of the base away from the right angle. So the right angle of the triangle is here. 1/3 of this distance will give us 2 feet. Therefore, it's 4 feet from A. If our distributed load here was like water, or probably snow would be a better example, or sand, what we could do is we could take this entire section of sand, put it into a single column. It would weigh 1,200 pounds. And if we place that column in the center here, and then we do the same thing over here, we take all the sand in the triangle part, stack it in a column, it's going to weigh 450 pounds. And if we set it here, the effect on the roller, the effect on the pin is identical to when the sand was distributed. So externally, we haven't changed anything. The beam, though, does know the difference between how we're modeling it here and when it's distributed, and we'll talk about that later. Questions on simplifying the distributed load into these point loads located at their equivalent locations. Now the problem looks just like it did in Chapter 5. We have one object. We have now just 2 point loads acting on it. So we can write the equations using the model that we've created. So in the x direction, we get bx is 0, one of the unknowns we're looking for. If we sum the moments about b, I simplified our distributed load into 2 point loads. We'll have 1200 times 4 plus 450 times 10 minus 14 AY. AY will get 664 pounds. Finally, summing forces in the y direction, AY plus BY minus 450 minus 1200. So exactly like we do in Chapter 5, we'll get a BY value now of 986 pounds.